This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Week 5, Lesson 9. Mechatronics, Motors, and Engines. Every component we've built this week has to be driven by something. This lesson is a breadth tour of those drivers: the electric motor, the internal combustion engine, and the sensor and controller loop that ties them to the machine. It's wide rather than deep. The handbook prints a compact set of motor and engine relations, and where it stays silent, we'll flag the item to memorize. Concept 1. The electric motor's electrical picture. The handbook keeps the bookkeeping simple. Efficiency is useful shaft output over input, and one shaft horsepower is 746 watts. Power factor is real power over apparent power. Direct current and some AC motors run at unity, but the common induction motor lags. Full load current follows from horsepower, efficiency, voltage, and power factor. Both efficiency and power factor derate the machine. The line delivers more than the shaft power alone. Concept 2. Torque and speed. Full load torque is fixed by horsepower over RPM times 5,250 for pound-feet. Watch the constant. It's 5250 here, not week 4's 5252. Same family, different number. Synchronous speed is a lookup by pole count. 2, 4, or 6 poles give 3600, 1800, or 1200 RPM at 60 Hz. The formula behind that table, 120F over P, isn't printed. Memorize it. And a real induction motor runs just under synchronous speed. That gap is the slip. Concept 3. Phases and heat. For the same horsepower, three-phase supply draws 1 over root 3, the line current of single phase. That root 3 is the only difference across the table, and it's the 1.73 you see spelled out elsewhere on the page. The table inverts to give kilowatts, kilovolt amps, or horsepower from current the same way. And a side note from the HVAC chapter, a motor's inefficiency shows up as heat, larger for a less efficient machine. Worth knowing exists, not worth memorizing. Concept 4. The internal combustion engine kept to one slide. Mean effective pressure is net work per unit displacement, the average pressure that would produce the cycle's work in a single stroke. Horsepower is that pressure times stroke, bore area, and power strokes per minute, over 33,000, the same shape as ordinary horsepower. Power strokes per minute fold in the cylinder count and the strokes per cycle, and the compression ratio is the swept to clearance volume ratio. One relation. That's the whole engine footprint here. Concept 5. Mechatronics, the control loop. The handbook draws the line between open and closed loops. An open loop acts blind and can overshoot. A closed loop feeds the measured variable back to the controller, shrinking the deviation from set point. Every closed loop needs 3 parts: a sensor to measure, a controller to compare against the set point, and a control device, a valve, damper, heater, or variable speed drive, to act. A transmitter turns the sensor's output into a standard 4 to 20 mA or 0 to 10 volts signal. Op-amps and ladder logic are thin in the handbook. Setup: a 20 horsepower, 4-pole motor on a 60 Hz, 460 volt supply, with efficiency and power factor given, and a nameplate speed of 1750 RPM. We'll find its full load torque, its synchronous speed, and its line current on single versus 3-phase. Then a separate 4-cylinder, 4-stroke engine with a given mean effective pressure, bore area, stroke, and speed. Find its horsepower. Note the torque uses the running speed while the synchronous lookup uses the poles. The difference is slip. Solve. Part 1. Full load torque, 5,250 times horsepower over the actual running speed, comes to 60. Synchronous speed for 4 poles reads 1800 straight off the table, and the memorized 120F over P confirms it. The motor runs at 1750, about 3% of slip below synchronous, exactly what an induction motor does. Solve. Part 2. On single phase, the line current works out to about 42. The same motor on 3-phase divides by root 3, dropping to about 24.5. That's why big motors are 3-phase. For the engine, a 4-stroke fires once per 2 revolutions, so 6,000 power strokes per minute, and the mean effective pressure relation lands near 73 horsepower. Traps. 5 ways the drivers bite. 1. The torque constant is 5250, not week 4's 5252. 2. The poles table gives synchronous speed, but the motor runs below it by the slip. Torque uses the running speed. 3. The root 3 is 3-phase only. Misplace it and you're off by 73%. 4. Compression ratio is V1 over V2 equals V4 over V3. Read straight from the page. Don't invent V1 over V4. 5. In the engine horsepower, the strokes term already carries the cylinder count, so the bore area stays 1 cylinders. Quick recall. Efficiency and power factor set the electrical draw. Full load torque is 5250 times horsepower over RPM. Synchronous speed is a poles lookup. 2, 4, 6 poles give 36, 18, 1200 RPM. Line current follows horsepower, voltage, efficiency, and power factor, divided by root 3 for 3-phase. Engine power comes from mean effective pressure and geometry, over 33,000. And Mechatronics is the closed loop, sensor to controller to actuator. Memorize the 120F over P speed formula and the loop internals. The rest has a page. Next up, Lesson 10, Exam Strategy and Worked Component Problems. This lesson finished the Area 5 toolkit with the drivers of a machine. The capstone pulls the whole week together. A decision tree to name the component a problem is really testing. A lookup map of every verified handbook page, and 4 fresh multi-step problems across vessels, springs, vibration, and mechanisms or motors. Everything's at peprepengine.com. Cheat sheet, worked solution, and a quiz attached here. If the course helps, subscribe.
The full study guide with every equation and common exam trap is free at peprepengine.com. Link in the description. Machine design, HVAC, structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.